Hello everyone, this is a video demonstration for EE542 Lab 4, which is performance evaluation of a custom file transfer protocol under varied network condition, and we are group 13. So we'll go to the basic main objective of this project. The main objective is to explore the TCP performance under suboptimal condition and develop a file transfer system which outperforms the existing protocol like SCP and FTP. So the protocol overview is basically we are using an enhanced version of UDP for improved throughput, and the key feature is reliable file transfer. So what is the working principle? So at first, the transmission approach. The packets are transmitted from server and client at the maximum speed possible, and we are using UDP for for its benefit of low latency, and uh, then it's a very reliable mechanism. So after the first initial transmission, the client will actually check for if there is any lost packet and request it back, and server will uh, send it back once again. So this is the timing diagram. So at first the receiver will send a file name to the sender. Then sender will find that file name, and after that it will chunk it and send it to thread for a faster file transfer. Then it will send the number of packets, and after that the receiver will maintain an set with all the different packet IDs, and I'll go in depth later on the slide. So then the sender will start sending the file one by one packet at a time, and after the last packet is sent, it will send an end signal signifying the end of packet sending. And after receiving the end signal, the receiver will check its set, and then it will request the lost packet from client. Then the server will retransmitted the missing file, and after all the file had been transferred, the receiver will send a stop signal, which uh, which signifies that all the packets are correctly received, and it will stop the connection. So packet architecture and retransmission. So after the initial transmission, the receiver will identify any missing packet IDs and store them in a set. And the set is since we cannot send a set, so we'll copy that set into a vector and send it to the sender. The sender will promptly transmit the requested packet and ensure data integrity and completeness. So this is our architecture of a transmitted packet. So our each packet consists of three parts. The first one is packet index, packet size, and data itself. So how the receiver ensures that it has received every packet. So first, so we'll go after that. The first, after receiving the number of packets, the receiver will maintain a set with every packet ID, as you can see from ID 1 to nth ID. After the first initial transmission, it will just delete every packet ID received, right? So it is removed from the set, and after that a new set is formed with all the missing packet IDs, and that is converted into a vector to send information back to the sender. So here comes the performance improvement. So demonstration setup, a 1 GB file we are using for demonstration purpose. The completion protocol, once all protocol is successfully received without any loss, the client receiver send a stop signal to terminate the connection between the sender and the receiver. Memory management. The receiver file is dynamically copied into the main memory during the runtime. Data storage. The client store all the packet indices in an unordered set along with the vector that contains the packet themselves. File write time. After transmission is completed, the content of the vector are written to a file. So this is a file transfer from a local system. As you can see, it has received the file and this file size. So this is in AWS. We use MD5 sum to ensure the correct file is received from the both ends. So this is the question. Now I would like to forward the presentation to Vikram, and we'll show the video code demonstration. Thank you.
Start. Okay. Hello guys. Welcome back again. This is Vikram. So now I'm going to show how our FTP protocol server and client code make our FTP protocol work. So let's go back. Now just to show the code and just to show the code and explain it and test it out, I will do it in VirtualBox, and then uh, this video will be then followed by my friend's demonstration of testing this video out in a AWS environment. So between two EC2 instances, server and client, with a router in between them, and some uh, impairments to the network too. And we will test it. We will test out how our FTP protocol handles all those situations. So let's get back to it. So this is the code that I we wanted to discuss. This is our server side part of our FTP code, file transfer protocol code. So in the server side, what we do is it's just a simple C++ code. It's just simple socket programming. So what we have to do is we have to use a UDP. Mayank in the previous video explained how our FTP protocol works. So it's really simple. So you just have to convert that into code. So uh, you have your server, right? You have your server waiting and seeing for new connections, and client requests the file, right? Now the server should first search for that file, and if that exists, the server should send back the number of packets that the client should prepare, because it's going to be big if it's 1 GB file. So we have our buffer size here. So every packet will contain 9,000 bytes. Okay, you have the flexibility to change it to 9,000 or 1,500 or whatever you please. But 9,000 is not as 9,000 is a good value. system should wait this receive function. Okay, so if there has been absolute silence, it will wait for about 2.5, 250 milliseconds. This is 250 milliseconds. So it will wait for 250 milliseconds, and after that, it will move on. Okay, that's what it means. So you're setting, it's like a delay for the socket. Uh, as long as you don't receive any packet, it will have a delay of 250 milliseconds. And if you receive anything, then it will move on. Okay. If it doesn't receive within this timeout window, then it will also move on in that stage. But if it receives something before this timeout, good for the system. It will thing is really good. So it's just like a worst case scenario where you don't receive any packet, you will wait for about 250 milliseconds. So during the initial phase, the client will listen for packets, and these are just print statements that you could use to. We try to comment unnecessary print statements that help us for debugging, obviously, but uh, print statements will consume RAM, and if you're transmitting a 1 GB file, being really optimal, being really um, having a very manageable code with lesser print statements is very uh, proved really uh, proved less uh, violent, actually proved less for the system. It was proved very beneficial for us, because if you transfer 1 GB file with a system with 4 GB RAM, I think it will drink pretty much a very significant part of the RAM memory, so the system will get clogged down. So print statements would add to that. So uh, we don't want to pour uh, petrol to fire. So yeah, so commenting out unnecessary print statements is a really important action that we have to take for this FTP to work. Right? So once this is done, this is the else if is worst case scenario where if there is no packet, right? Probably it suspects packet loss, and it will break down out. It will break out of this while loop. So that's it. So the initial transmission phase is completed. Uh, so we can also go back to now you can go back to server. Right? So in the server side, during the retransmission phase, what happens is it has the timeout of 250 microseconds, and this max retrans attempts variable has a purpose which I will discuss very soon. So here there is a while loop. Okay, within this while loop there is a for loop. Okay, so what do they mean? Okay, so first, during the retransmission phase, once the server enters the retransmission phase, it expects the missing packet, indices from the client. Once it receives that, it will start processing it. So that is this loop, right? Till the missing packet indices gets over, you have to send all those packets, that those indices correspond to. So once that is done, you will finally expect a stop signal from the client, which indicates an acknowledgement from the client saying that it received all the packets, ending retransmission. You can end the retransmission. But if you don't receive anything, okay, if there's an idle, if it's just idle, the connection is just idle, that's where the timeout comes into play. So it will listen for 250 microseconds, and it will keep on exiting out of this loop, and that is where the max attempts variable come into play. So if it doesn't receive anything from the client, it will retransmit the same information that we transmitted, same number of packets, these packets that we transmitted, again, a maximum of 5 times. This is a design choice. You can keep it, you can have it, it depends. Like, the reason is maintaining what are the packets that we received and what are the packets we received. Very important. Um, using an optimal data structure will just be positive to us. We used an unordered set. The time complexity for removing or deleting an element from unordered set is low. We previously implemented a vector for this. Um, for a vector, it is powerful. So, uh, it set a significant contribution to our throughput. So it fastened this and it fastened this entire process for like about 3 seconds. So it was 3 seconds faster. So yeah, very significant, very significant improvement. Okay, so we keep this in set. Whenever the set is not empty, if the set is empty, good enough. In the first transmission, still we received everything. If the set is not empty, we did not receive the complete file. So that's that, and it will. The thing is, once it enters this loop, it will search for the missing packets, and yeah, so it will receive all. So one sec. So yeah, so this is the Server is ready, waiting for client is starting. It's pretty important that the server and the client they are the same port. 7010, 7010, yeah. I've got 119,000 packets. One sec. I think there's a fault we should handle. So sorry, there was a RAM issue. I had to upgrade my RAM so that I had two low RAM. So I upgraded it to 4 GB. So sorry about that. I did not incorporate it in this version. So this system. Okay, let me run the code now. So we were lucky. Yeah, okay. It occurred it encountered packet loss, and I think that was so it retransmitted the file. Now it transmitted the file completely. So with minimal retrying, I think because there were only 3 retries. So yeah, so that's it. And it took about 1 second for us to because in the code we have 1 second. So in the code we have a diff time of end to start, and this is end is here, and the start is about when we start requesting the file. Yeah. So it's about 1 second for us to transmit the entire file. This is fast because it is in the local interface. But if you do it in AWS, you will be heavily slowed down because of link losses. You know, probably there might be wireless links too between two machines. I don't know much about that, but if there's wireless link, then things get extraordinarily complex, and they are in a different realm. So the congestion might not be the biggest factor for packet loss. It might be just back channel, and that's just 99% of the cases in the wireless. So, uh, yeah. So that's it. It's for our demonstration of our code. So every thread sends that file and it chunks it, and the client just receives all the packets in one socket. That's it. Yeah. Okay.
Yeah, so in this part of the video, we'll be performing the demonstration for the file transfer protocol that you designed. Considering the technical aspects of the VMs being used, that is the instances being used, we're only using a limited amount of file memory that we are transferring, which is around 1 MB. So here, in this case, we have performed from the first case 1 till case 3, we have initially sort of the basic settings that are to be done using the sudo tc qdisk command. So after completing the setup for the first case, the bandwidth for TCP and UDP are shown here. So for TCP, it's pretty less, but for UDP, we have a very good bandwidth, but then the loss in datagrams is very, very significant. It's like 50% of the data that's being transferred. In this case, we perform the file transfer protocol, and then we get it within very less number of time. It's around 0.3 to 4 seconds. For the next case, we've increased the delay, we've increased the drop rate to 20%. So this is being reflected in the UDP's bandwidth. Like we lose around 61%, which is more than 52% of the data that we had previously. After that, we perform the file transfer protocol again. So this time it takes around two seconds because the time taken after dropping and then retransferring packets has taken an extra time. So it takes around 2 seconds. Then we perform the ping operation to check if the time taken is around 200 milliseconds from one side to another. To avoid time constraints, we have already run the program here. After that, we have changed the settings for the third case. So all of these are listed here. I already configured all of the settings here. So after reducing the transfer rate to 80 bit mbit, and then setting a delay of 200 ms. So we perform the file transfer protocol again, and then we are obtaining the time around 3 seconds. So now we'll perform the MD5 sum. Yeah. Now, after performing the MD5 sum, we observe the file that is being transferred to the client is the same file that we have in the server. So this demonstration shows the functioning of the file transfer protocol that is being discussed. And that concludes the experiment. Thank you.